Hey everyone, in section 1.2 we talk about the properties of exponents. An exponential expression is a mathematical expression of the form c times a raised to the n. Here we're referring to a as the base, the number n is the exponent, and c is some possible constant multiplier on the outside. As an example, consider 7 times 2 to the fourth. That 7 is not being taken to a power of 4, only the 2 is. So this becomes 7 times 2 to the fourth, which is 7 times 16, which is 112. Next, consider negative 3 to the third power. That negative is inside the parentheses, which means that that power of 3 applies to it. So this expression is negative 3 multiplied by itself 3 times, which will yield an answer of negative 27. And our last example is negative 2 to the fourth power with the negative outside. So I multiply negative 2 by itself 4 times, which gives me positive 16, but that negative sign outside survives, and it acts like a multiplication of negative 1. So I get a final answer of minus 16. So the key takeaway with this type of example is that the placement of our negative signs inside or outside the parentheses does affect our final answer. It is true that if I take a negative number to an even power, the final answer will be a positive number. But if I have a negative constant outside of that exponent, then my final answer need not be negative, as it is in example 3. Next, let's talk about a couple of important cases. If I take any real number a not equal to 0 and raise it to the power of 0, I get an answer of 1 by definition. However, the number 0 to the 0th power is undefined, kind of how the number 1 divided by 0 is undefined. Think about it for a second. What exactly would it mean to multiply 0 by itself 0 times? The notes of this video does provide some justification or reasoning for this, but just know that when we ever see 0 to the 0th power, we tag it as undefined. Next, we're going to display a list of powers of 2, 3, and 5. The idea is that in practice, recognizing numbers as powers of 2, 3, or 5 becomes very useful when we're doing a lot of algebra. And these particular numbers do come up pretty frequently, so it's good to be able to recognize them as powers of 2, 3, or 5. In this next slide, we're going to study some rules of exponential arithmetic. Take 7 squared times 7 to the third. If we fan out the number of 7s that we have, we notice that the exponents actually add with one another. Next, take 7 to the third divided by 7 squared. Fanning everything out and observing some cancellations, we notice that the exponents seem to subtract from one another. And if I take the reciprocal of this fraction, it turns out that I get 1 over 7, which can be interpreted as a negative exponent. Here's a list of exponential properties that can be thought of as simplification laws. So let a and b be some non-zero bases, and let m and n be exponents. Our first rule says that when I multiply two exponential terms with the same base, the exponents add with one another. Our second rule says that when I divide exponential terms with the same base, our exponents subtract one another. And our third rule tells us how to work with negative exponents. Typically this means changing my location in the fraction. Our other rules are displayed as follows. Rule number 4 says a power to a power means multiplication of the exponents. Rule number 5 says when I have a product of things raised to the nth power, that power of n applies to both a and b. And the 6th rule says that we have a similar rule as number 5, it just applies with division. And also, with the second part of rule number 6, this means that whenever I have a fraction to a negative power, applying that negative sign from the exponent reciprocates my fraction, or turns it upside down. In this slide, we talk about something that is typically a very common mistake in any kind of algebra class. Notice that there was no rule that said a plus b to the nth power was equal to a to the n plus b to the n. Because of rule number 5 on the previous slide, this is typically a very tempting thing to try to do, but it turns out it's not true in general. There is a formula for a plus b raised to the nth power, and this is given by something known as the binomial theorem, which is expressed as follows. Obviously, this doesn't look like a very nice or user-friendly result, comma. It just means to say that there is a rule for a plus b to the nth power, it's just not as nice as one might think. A way to justify this to yourself is that whenever I'm dealing with terms like a plus b to the second or to the third power, it typically means multiplying this out or FOILing out. And we'll see how to deal with expressions like this in section 1.3. But the moral of the story is that exponents do not distribute over sums of terms. Now let's look at a few examples of simplifying exponential expressions using these rules. Suppose that I have x to the 7th times y to the minus 3 times z to the 11th divided by x to the minus 1 times z to the 9th. The general strategy for a problem like this is to start matching terms that have the same base. So I want to deal with those two copies of x's raised to different powers and subtract their exponents. I'll also do the same thing with the exponential terms that have z as a base. So combining those, I get x to the 7th minus negative 1, y to the 3rd is by itself, and z to the 11th minus the 9th power. Notice that I subtracted negative 1 from the 7th in that z term. You have to be careful about negatives that are already embedded into the problem and not to drop them. When I simplify the terms in the exponents, this becomes x to the 7 plus 1, y to the minus 3rd, and z squared. I'll simplify the exponents further to get x to the 8th, y to the minus 3rd, z squared. Simplifying a problem like this means that I don't want any negative signs in my exponents. Since I have a y to the negative 3rd, I want to change that into 1 over y to the 3rd. So the final expression I get will be x to the 8th times z squared divided by y to the 3rd, and we're done. No negative exponents, no repeated variables, and we are complete. Remember that a negative exponent means changing my location in the fraction. So when I am simplified completely, I need to move things around either to the numerator or denominator if they have a negative exponent. In our next example, we're going to view something a little bit larger. Now I have a big fraction with a lot of terms raised to the power of negative 2. Our exponential rule says that a power to a fraction that is negative means I can flip or reciprocate the fraction. So I'm going to apply that negative, and I'm going to flip my fraction upside down and leave my exponent of positive 2 on the outside. The next step is just to now clean up the inside. That constant term, negative 3, I want to separate as negative 1 over 3. Next, just like I did in the last example, I want to combine all terms that have the same base. So I have an a upstairs and a downstairs, a c upstairs and a downstairs, so I can subtract their exponents, and my b I can simply move up to the numerator because of its negative power. Now I'll simplify the terms inside the exponents to get the following. The entire quantity inside is one product, so I can apply that power of 2 to each individual factor. We'll continue this example on the next slide. Now that we've got the following expression, we can apply each power of 2. Remember that a power to a power is the same thing as multiplying the exponents. So when I apply those operations, I obtain the following. 1 over 9 times a to the 8th times c to the negative 10 times b to the 4th. Now that I have no exponential terms with the same base, I can start moving terms around based on the sign of their exponent. The only thing I need to bring down to the denominator is that c to the minus 10th. So this becomes 1/9 times a to the 8th times b to the 4th over c to the 10th. Lastly, since I have a multiplication of fractions, I can simply absorb these numerators and denominators together. So I get a to the 8th times b to the 4th divided by 9 times c to the 10th, and we're done. We'll end this video with an example that's a little bit more challenging. Consider the given expression. Even though it looks like there's a lot, there's one term that sort of goes away for free. Notice 18 times x to the minus 3rd has a power of 0, so by definition, that term reduces to 1. Since each term has a negative exponent, we can change each term's location in the fraction. This is going to give me xy to the 2nd divided by negative 2x3y to the negative 1 to the 3rd power. Again, all I've done is changed each term's location in the fraction to take care of the negative exponents on the outside. Next, we're going to apply that power of 2 to the x times y, and then that power of 3 to the quantity downstairs. Since everything inside these parentheses is a product, we can apply those powers to each term within. This gives me x squared times y squared divided by negative 2 to the 3rd times x to the 3rd to the 3rd times y to the negative 1 to the 3rd. That minus 2 to the 3rd will become negative 8, but our other terms exercise the ability to take a power to a power and turn it into a product of exponents. This results in the expression x squared y squared divided by negative 8 times x to the 9th times y to the negative 3rd. Now that these outermost exponents have been taken care of, we can simplify this problem like we did in the two previous steps. Let's first perform our exponential subtraction to get negative 8 times x squared minus 9 times y squared minus negative 3. This will simplify to negative 1 over 8 times x to the minus 7th times y to the 5th, which will then simplify to the final answer of negative y to the 5th divided by 8 minus x to the 7th, because we moved that x to the 7th downstairs because of its negative exponent. The examples in this video definitely took a little bit of work, but that's okay because we want to show a lot of variety in what can happen. Take a moment to watch these videos again if you need to, or look at the notes associated with these videos to get a better idea of what's going on with these examples, especially if it didn't click the first time. Thank you so much, and join us for our next video on section 1.2 for scientific notation.